Yeah, okay, good. So Venkat is at the conference, I think, and Anirudh is in the room somewhere. Um, great, yeah. So let's look a little bit about how stabilizer codes work. So imagine you have a bunch of qubits. One of these qubits might be corrupted at some point by an error. What a stabilizer code is going to do is that you're going to perform some measurements. So like here you have M0, M1, and the point of these measurements is to identify where the error is to potentially correct it. Um, oh, okay, good. Oh, fuck. Um, I don't think it's the right version, but okay. My bad. So, right, these measurements are going to define the code and its properties. Among all the properties we can consider, we're going to focus on three of these, which are n, the number of qubits you use in your system, k, the number of qubits that are protected, and d, the size of the smallest error that you cannot detect. Great. So because you might have different measurements for different codes, you have different connectivity structures. For example, codes might live in different dimensions. We've heard a whole talk about this. So a natural question is like, how does that impact the performance of your code? And it turns out that codes in lower dimensions are known to perform poorly. As it was mentioned before, this is was proven by Bravi Pulentahal in a series of work. And we know that the distance is bounded when they live in low dimensions, and you also have a trade-off between k and d. Right, so now that those bounds exist, it's not entirely clear why a lower dimensional space is bad at protecting quantum information. Um, it's also not clear once you have these bounds how to generalize them to other spaces because the techniques are quite specific to the Euclidean space in particular. And all these bounds kind of like point to a notion of connectivity in a way that is important in some way, but it's not entirely clear how to define connectivity or how to quantify it. And on the other side of that question, there's also the fact that there has been a flurry of good codes these last years, and they all rely on codes that are extremely connected. And we would like to know to what extent that connectivity is important, and the kind of ultimate question we want to answer is like, what makes a good code good? Is that precisely this connectivity? Um, Great. So in this talk, what we're going to try to do is first quantify connectivity for quantum codes. And second, from this notion of connectivity, we're going to try to bound parameters of quantum codes. The notion of connectivity we'll use is that of the separation profile, and I'm going to explain it to explain what it is. But before doing that, I'm going to explain the connectivity graph of a code. Yes. So here you have an example for the surface code. So the connectivity graph of a code takes maps qubits to vertices. Like here you have like for every qubit, you have a vertex, and secondly you have an edge between any two qubits if they are involved in the same measurement. Great. So now that we have this notion of graph for a given code, we can introduce the separation profile. Now, some graphs have a particularly uniform structure. So like if you look at this 2D lattice, for example, I can remove approximately square root of n qubits and divide it into two roughly equally sized parts. Now, if I zoom into this graph, I can kind of do the same thing. And yeah, if I zoom further into it, then I can do the same thing again. So like there's something that's quite uniform about this graph, for example. Yes, and okay. So you can see that the amount of qubits that you remove at every step corresponds to a certain function of the subgraph. And the point is that the function never changes. So like across the graph, across the scale that you're looking at, it's always the same function that indicates the amount of vertices that you have to remove. And this kind of graph is called S-separable, where S is the function and S is the separation profile. Great. So previous results have focused on what happens when S is polynomial. So S is bounded by R to the C, where C is a constant strictly lower than 1. And the results have been that D is upper bounded by some quantity, and there's a trade-off between K and D. Now we have some new results. No, that's not it yet. Great. Natural question. How tight are these bounds? We have really relatively good indication that the distance bound is pretty tight, but we know for sure that the KD trade-off isn't. Now, those new results that I'm presenting here, we're presenting a new trade-off between K and D, and this time it is a little bit closer to being tight. It's not quite all the way there yet. So I'm going to give you an example. Let's look at how these bounds apply to D codes. On this graph, you have the x-axis is log n of k, the y-axis is log n of d. The dark shaded area here is the range of parameters that is allowed by the BPT bound. You can see that this more light area was the area of parameters allowed by the previous bound. And you can see that it's quite, like it allows a lot more than the BPT bound. Like it's not very good. Now this work introduces a new bound, and we're kind of like halfway to closing the gap with the BPT bound. Great, so to explain how these bounds work and how we can prove them, I'm going to introduce some tools. So the first one is the idea of a correctable region. So a correctable region is a set of qubits such that I can lose those qubits entirely. I can like trace them out entirely, and I can still recover them. And something that's quite notable about those regions is that out of small correctable regions, I can compose bigger ones. In particular, so if I have U and U prime that are correctable and like they don't share any edges, then the union of U and U prime is correctable. Similarly, I have what's called, so this is called the union lemma. And I also have the expansion lemma, where if U is correctable and its boundary is also correctable, then the union of the two is also correctable. The final technical lemma I'll use is that for any code, if I can find a tripartition of the vertices where A and B, so like here you have A and B, if these two regions are correctable, then the number of encoded qubits in the code is upper bounded by the size of C. Great, so now how do we find those big A and B correctable regions? I'm going to give you an example of how the BPT paper addresses the question for the case of 2D codes. Great, so imagine that you have a code whose distance is pretty large, it's bigger than 1. Then you can take any arbitrary qubit in the graph, and that qubit will be correctable. Now, I can also look at a bunch of far apart qubits, and because they're quite far apart, like each of them individually is correctable, and because they're quite far apart, I can use the union lemma, and this whole region is now correctable. Now, what I can do is observe that if the distance is large enough, then these boundaries are also correctable, and I can use the expansion lemma to grow my region. So I obtain larger and larger correctable regions until I reach the point where these boundaries have size D. Great, and I obtain a massive correctable region. One way to quantify how good your partitioning is to look at the size of what's not in the region, so like the complement of A. And in the case of the BPT bound, the complement of A scales as n over D. Great, now the last step, we're almost there. You can convince yourself that these little blue strips, they're of size roughly D, so like with the right scaling and everything, each of these individually is correctable, and they're not connected because there's a gap here. So I can use the union lemma, and this whole region is correctable. Great, so now I only have to find the region C. The region C is whatever is left, and I have my region C. So if you look at a larger lattice, for example, you'd get a similar pattern, and Without partitioning, you get that the region C scales as n over d. So pretty good, actually optimal. Great. How does that work when you only have access to the separators? So in the previous results, the way that the bound is proved is that you look at your lattice and you take out a separator. And so you end up with like two regions that are roughly equally sized. Now, you can look at whether these regions are smaller than D. And if they're not, you can continue separating them. You separate them over and over again until you're left with a bunch of tiny regions, and each of them is smaller than D. And because they're all smaller than D, and so they're correctable, and because they're all disjoint, we can use the union lemma. And so we end up with a massive A region. Now, the problem with this technique is that we never use the expansion lemma, which is bad because we end up with a suboptimal partitioning. Like in the previous case, we had the complement of A scaling as n over D. In this case, we have the complement of A scaling as n over square root of D. How do we obtain region C? We do essentially the same thing. We look at the blue region here and we recursively partition it until we are left with a bunch of disjoint sets of size D. And because they're disjoint and smaller than D, then they're correctable. Great, so how does the new partitioning work? So the main improvement was trying to find regions that are bigger than D and are still correctable. Now, how do we do that? We look at regions that satisfy a few conditions. So if you look at this subgraph G prime here, so like the teal shaded region, this region we require that it has a relatively small boundary. Here the boundary is in orange. The boundary is smaller than D, and also G prime can be much larger than D, but it still has to be small enough that its separators are going to be smaller than D. Great. And so once I have these conditions, I'm going to start separating my graph. I recursively separate it again and again until I get a bunch of disconnected regions that are all of size D. Great. Now I would like to go back a little bit. From this, I would like to be able to show that this region here is correctable. And how do I do that? With the expansion lemma. If you remember, the partitioning gave us these two regions, for example, that are both of size smaller than D, so they're correctable. And I could use the union lemma and show that the union is correctable. But I still have this gap in the middle here. I have to like add these qubits to the rest of the correctable region. And the way I can do that is using the expansion lemma on this whole boundary there. Now to do that, I have to show that this region there, so the boundary is correctable. And to do that, I'm going to need to upper bound its size. How can I do that? Well, I can note that this boundary is included in this in the union of this separator, and then the previous separator, and the previous separator again, and the overall boundary. Now, something that's quite nice about recursive partitioning is that at every time step, we divide the size of the region by 2. So actually, the size of the sum of the separators when we go up the levels is dominated by the size of the first separator. So we get that this boundary here scales roughly as the separator of D. And because we required the separator, the separator of G prime, and because we required that this is smaller than D, then we can use the expansion lemma. Great. Now that we have that, we can bubble up through the graph. Okay, you can bubble up through the graph and show that this is correctable, and then this whole thing is correctable, and same thing on the other side, and then the whole thing is correctable. So you do end up with something that is correctable, even though it is much larger than D. How do we apply that? Well, we're going to separate our graph until the regions are not of size D, but are sufficiently small such that the separators are of size D. Once I do that, most regions are going to have boundaries that are relatively small. And in those cases, we can apply the lemma that we've just seen. But in some cases, the boundaries are going to have a weird shape. And in those cases, I'm going to do something very simple. I'm going to keep dividing them until they're made up of small D-sized regions. Because there are only a few of these weirdly shaped regions, it doesn't cost us too much. It costs us about n over d vertices. And the blue region, you can compute it. It also has about n over d vertices. And now we can obtain our A region. Something that's quite interesting is that this partitioning method seems to be good enough that we recover the BPT scaling for the complement of A. So that's quite nice. Now, how do we obtain the region C? We do the same thing as before. We recursively separate the blue region until it is made up of disconnected subgraphs of size D that are correctable. And the final result is that we get a region C scaling as n over d to the 5. Great. So this is essentially how these bounds work. Some future directions, if you want to think about it, is like whether this connectivity metric can actually cover BPT in any way, and how to separate the grafters of the first partitioning, because as I've mentioned, it seems like at this step we're doing something pretty optimal, and the step that seems to be not optimal is how to divide the blue subgraph. That. Thank you.
Okay, any questions? Good.
Hi, thank you for the talk. So you had this very nice example with the surface code going through the slides. I was wondering if it is a hard problem to find the separation profile for codes that have long-range connectivity rather than the surface code, or is that a simple algorithm?
Usually, yeah, it's pretty hard.
All right.
It's not really something you can do in practice.
And do we have any, do we need to do it in practice, or do we need to find just the upper bound that you mentioned?
No, so like, yeah, usually those bounds are very much for like, if you know that your graph lives in a specific space, then you can apply this method. So for example, if you know that your graph lives in the 2D hyperbolic plane, then you can apply it and yeah, you obtain a bound on its parameters.
All right, thank you.
Welcome. Hi.
Do you think you can, like, is the separator profile, do you think that that's a fine enough grain tool to recover BPT, or could there be some gap that you need some extra assumptions in order to get it?
That's a really good question, and I have no idea. So like, at first I was pretty pessimistic, and then we found this improvement. So I have no idea. I think like, so the main blocking bit actually is when you get to this point, the graph that you're left with, the blue thing, its separator is significantly smaller than what you had before, right? So like, if you could somehow show that once you've removed all those bubbles, then the separator decreases drastically in size, maybe you could recover BPT. So I don't know.
Thanks.
Good question.
Okay, any further questions from the audience? So if not, we can end the session and thank all the speakers.